don't know if it started. Hello, everybody. We are going to start today by creating an HR diagram, and we are going to talk about the HR diagram and show you some other nice pictures of the HR diagram that I didn't do. But first, I would like you to write this also. Let's make an HR diagram right now, just to start, because the HR diagram is going to be very important over the next few classes, maybe even more. And so let's begin here. So for our HR diagram, let's show our axes here. And we have temperature getting hotter this way, right? Remember, we have the O, B, A, F, G, K, and M stars. These are cool. These are hot. We also over here have absolute magnitude getting bright, so high luminosity. And here's low luminosity for stars. Remember, we put numbers here, 20, 15, 10. We're getting brighter as we go this way. Remember, 20 is very, very faint. 5, 0, -5, -10. All right. So now let's put in our groups. Well, we put, remember, the sun was a G2 and a 5, which we talked about right about here. But we also, that's a little high, the sun was probably about right there. And we also have all these other stars on this region known as the main sequence. So remember, we have the main sequence here. We also have stars in this region that are larger stars that are called the giants. We have even larger stars here that are known as the supergiants. And we even have stars here that are the white dwarfs. So again, main sequence, giants, supergiants, and white dwarfs. So that's my picture. That's my HR diagram. You do your own. You do as well as you can. Just sketching it out so we're going to get to know these regions. Now, I want to share the screen here because I want to show you some good pictures. I mean, your picture might be good, your diagram, mine's not. But let's take a look here. And here is a decent HR diagram showing the main sequence, showing giants right here. There are the giants, supergiants up here. Here are the white dwarfs, showing the colors too. Look, reds, orange, yellows, whites, blues for the temperatures. Remember, the temperatures are here in kelvins. If you want to know in Fahrenheit, you don't have to. 3,000 kelvins is approximately 6,000 degrees Fahrenheit, a little bit less than 6,000 degrees Fahrenheit, really multiply by 1.8 and not 2. But for high temperatures, multiply by 2, and it's close. 6,000 kelvins would be about 12,000 degrees Fahrenheit. There's 25,000 kelvins, about 50,000 degrees Fahrenheit. That's surface temperature of the star, the outer gas temperature. Surface, even though there's no solid surface, it's the outer gas temperature. Also on here, look at this. It's listed not just the spectral types, which you have to have on an HR diagram. Sun would be here at a G2. There's the sun, G2. Remember, everyone starts at 0 and goes to 9. And the sun's absolute magnitude is 5. There it is. But remember, we also said this. If it's a absolute magnitude 5, here's what we're going to call it in luminosity. I don't know if we exactly said this, but it's 1 solar luminosity. So a star that has an absolute magnitude, which is its true magnitude, if it were 10 parsecs away, how bright it would be on the magnitude scale, it would be a, if it's a 5, absolute magnitude, it's called 1 solar luminosity. It's the same energy output as the sun. Pretty much the same type of star as the sun, probably, if it's producing the same amount of energy. Now, what if something were 5 magnitudes brighter? I mean, remember, that's brighter. 0 is brighter than a 5 with magnitudes. It's the opposite. So as you get smaller number, it gets brighter. If it's a magnitude 0, remember we said every time it's 5 magnitudes in difference represents 100 times in brightness. So look at this. If it's magnitude 0, it's 100 times in luminosity, or 100 times in brightness. So there are stars like this star Regulus, or about Vega, that are in actuality 100 times brighter than the sun. They give off 100 times more energy. What if there was a difference of not 5 magnitudes, but 10 magnitudes? It would be 100 times 100, not 100 plus 100, 100 times 100, which is 10,000. So a magnitude minus 5 absolute magnitude star like Betelgeuse or Antares, which are actually supergiants, are really 10,000 times more luminous, give off 10,000 times more energy than the sun. What if we're another 5 magnitudes brighter? Well, it's 100 times 100 times 100, 10 to the 6, or 1,000,000 times brighter, 1,000,000 times more luminous. So really, the only thing I really wanted you to know from this, for every 5 magnitudes, it's 100 times in brightness. That's good enough. We already wrote that down. Well, take a look here. The stars like Betelgeuse, Antares, or supergiants, red supergiants. Deneb's a white supergiant. Rigel's a blue supergiant. Turns out Rigel's very, very massive. More massive than Betelgeuse. Betelgeuse is only about 16 times the mass of the sun, but Betelgeuse is about over 1,000 times the diameter of the sun. So it's very, very spread out. Supergiant star, very, very large. You have these stars: Arcturus, Aldebaran, Mira, Pollux, giants. Then you have these stars' main sequence. Look, Altair, Sirius A, Vega, Regulus. And then down over here, well, here are the red dwarfs. Very, very common stars. Look at this: Procyon B, Sirius B, white dwarfs. Some of the white dwarfs are actually bluish in color. They're blue dwarfs, but we call them white dwarfs. Well, that's a nice HR diagram. Look at this HR diagram. Oh, that's not an HR diagram. This is something I'd like you to know. Luminosity classes. Luminosity classes. I want you to know 3 of them on here. You see number 1, Roman numeral 1, supergiants? Should write that down. See Roman numeral 3, giants? Write that down. Roman numeral 5, main sequence. Write that down. Forget the rest of them. Don't worry about the other ones. There's these other classifications for bright giants, subgiants. I just want you to know supergiants, giants, and main sequence. What this is telling you is what type of star. Now let me show you how this works on the HR diagram. So on the HR diagram, what we're going to do is label main sequence as luminosity class 5, Roman numeral 5. We're going to label giants as luminosity class 3. We're going to label supergiants as luminosity class 1. It's a 1, Roman numeral 1. 1, 3, 5. So watch this. I'll show you how this works. Let me use the sun as an example. I don't know. That's on the G2. I don't know. Let's put the sun right here. I already put the sun. Well, I'm just going to say that's. Yeah, let's call that the sun. All right. So let's say that's the sun right there. Sun. It's a G2, right? See that? Go up straight from there. G0, 1, 2. Go straight up. It's a G2. It's also a magnitude, absolute magnitude of 5. See that? So how would you designate this, a G2, and forget about the 5 there. How would you designate a G2 star in the main sequence? It would be a G2 luminosity class 5. That's how you'd write it. So if I were to say what star is a G2-5 here, well, I mean, it could be one of these two, but it would be something, there would be the sun. But watch this. What if there was something right here, right above the sun? Isn't that also a G2? But it wouldn't be a G2-5. It would be a G2 with luminosity class 3. That would be a G2-3. So the G2-5 is the sun, but the G2-3 would be that, which means a G2, but a giant. What if there were one right here? Also a G2. Same temperature, surface temperature. But do you see where it is? It's in the supergiants. So what would that be? I'll put that over here. This would be a G2 luminosity class 1. G2 luminosity class 1. So you see that? I'd like you to know that, because I am at some point, I might want you, I mean, I might pick some stars out here. I might say there's an A5 star right over there. There's an A5, right? A 0, 1, 2, 3, 4, 5, something like that. And I might do this. Here's an A5, but I might put a star here. And I might put a star here right above the A5, like there and there, and say, there's star A, here's star B. And I might say, which one would be the A5 luminosity class 1 star? Which one? Would that be A or B? Well, if it's A5 luminosity class 1, you see it would be a supergiant because it's luminosity class 1. So that's what that would be. So I just want you to be able to see that there. All right, so that's luminosity classes. So let's share again here. So let's see maybe another HR diagram. Here's a nice HR diagram showing luminosity over here and solar luminosities. Here's absolute magnitudes. Here's the temperature classes. And so there's the main sequence, giants, supergiants up here. There are like bright supergiants, not as bright supergiants. So there's further classification. You don't have to worry about that. Look at this HR diagram. It's kind of making, I mean, this is kind of a nice artistic HR diagram. However, I don't know if it's the best one, because you know what? It's showing stars on here. So really, HR diagrams should be points that represent stars. You shouldn't actually put the real stars on there because it's a little deceiving. I mean, it's kind of nice where you have the red dwarfs here and they're named here. There's the sun, and here's the main sequence. Here are the giants, supergiants, white dwarfs. But in reality, this line right over here represents 1,000 times bigger than the sun. So if a star is in the upper corner, upper right corner is going to have the largest diameter stars, largest diameter. Well, the Betelgeuse and Antares are really 1,000 times the diameter of the sun. On here, look at the size of the sun. Are these really 1,000 times across? No, 1,000 times. No, you can't do it. There is one other HR diagram that I'll show you. I think I'll show you. It's a really nice one, but it's a little more accurate if you want to put the stars on here. Really, it shouldn't be the stars because it's really hard to represent the actual sizes on here. Well, anything along this line, 1,000 times bigger than the sun. Along this line, 100 times bigger than the sun. Along this line right here, it's hard to see that line, is 10 times bigger than the sun. And what about if it's on the same line the sun's on? Yeah, same size of the sun. White dwarfs, about 1/100th the size of the sun, about the size of the Earth. This is a nice one. It shows mass. Look, 5 solar masses for a star here, 10 solar masses. The sun is 1 solar mass. So it shows solar masses here, the mass of the star. And there's some nice red dwarfs over here, these low mass stars. So that's a nice one. Nice HR diagram. Look at this. Here is a real HR diagram with real data showing that there's so many red dwarfs. And here is the main sequence. Here are the giants. Here are the supergiants, and here are the white dwarfs. So this is the real data. So you see nature is not quite as clean as the way we're writing it. But you still can kind of see the patterns here. The main sequence is still the most common. You know, a lot of giants, some not as many as main sequence, supergiants, and white dwarfs. So now, I want to talk about this HR diagram. I want to go back to our video. And I want to ask you a question here. Why are stars, I mean, what does this mean? Look at this. Most stars are in the main sequence. There's some stars really big, supergiants. They're pretty big stars, a lot of giants, but they're not as many as the main sequence. And there are some stars that are very, very small. If I were to ask you what this means about stars, why would a star be here, like in the main sequence, while another one's here, while another one's there, while another one's there? What would your answer be? Why would you think this? Is this just random? If it were random, why would 90% of the stars be here, right? You wouldn't, if it's random, wouldn't there be equal amounts in every category? So there's something going on here. What do you think this represents? Let you think about it. Might it be the evolution of stars? How stars evolve? If this is the evolution of stars, let's go on this for a while. Does that mean this? Let's say this is how stars evolve. Does that mean that stars start like people and little animals and plants start small and then eventually get bigger? So a star will go from here to here, main sequence, to giant, to supergiant? Is that what that means? Or do they start big and get smaller and smaller and smaller? I don't know. I mean, or is it something else? All right, it's kind of hard to tell, but here's what I want you to do tonight. If you get a chance, go outside and find the star, let's say Vega. Let's call this Vega. It's a bright one in the summer. It rises pretty early. It's up there if you go out like at 11 o'clock at night or 10 or 11, I mean, as soon as it gets dark, it's getting pretty up there, kind of probably be in the to the east star. And it's in the main sequence now. It is in the main sequence. I want you to tell me how that star changes over the next few days before, let's say, next week, or I don't know, how it changes. Is there going to be a problem with you seeing it change? I mean, it might rise and set, which it would, but is it going to look different? Is it going to look really a lot brighter? Do you think it's going to become a giant? It's going to become a supergiant in the course of that time? Is it going to become a white dwarf? Probably not. Now, what if I gave you a little more time? What if I gave you a whole year? Think it'll change? No, probably look the same. What if I gave you 100 years? Nope, look the same. What if I gave you, let's say, hundreds of thousands of years? No, probably look the same. I would have to give you probably billions of years for you to look at it to see if it changes. Probably billions of years. You don't have time for that, not during the summer. Well, if I gave you, let's say I gave you a kitten. If I gave you a little kitten, and I wanted you to plot, probably not its temperature like we're doing for stars here. Kittens don't like that if you're checking its temperature every day. Let's say you plot its weight versus its height over the course of a year. You'd see changes. Yeah. What if I give you a little little plant, like a little, I don't know, tomato plant. You plant it, and over the course of a year, you're going to see, let's say, plot its height versus, I don't know, like how many tomatoes or how wide it gets. You think it would change? Yeah. Yeah, it'd change in a year. Change quite a bit. What about even a kid that's just born? That kid gonna change in a year? Yeah. But for stars, we don't have that luxury. We have to wait millions or billions of years to really see any difference. So how are we gonna know what's gonna happen to Vega over time? I mean, it would be nice to know. How do we know what's gonna happen to the sun? How do we know how they got there? How do we know what they're gonna do next on here? Well, we have devices that actually do things for us very quickly. And you use them all the time. And you're probably using one now. What do you think they are? Computers, right? Your phone, computer. We use computers all the time. And computers do things very quickly for us. We can figure out things fast. I mean, if you put the word cat into a Google search, within a few seconds, you're going to get, say, 1 to 20 of 680,000 different sites or something that have cat in it. So let's do that for stars. Let's go to a computer. All right, let me show you a computer. I don't know, I'm just gonna show a computer like this. Say like a tower, I don't know. If you're not sure what this is a computer. And we're gonna ask this computer, okay, computer, tell us how stars evolve. What is the computer gonna do? Yeah, you ever try to talk to your computer like that? Computer, tell me this. I mean, usually you have to punch in. If you get a new computer that really has just been made, does the computer know everything right away? I mean, no. Well, how does the computer know stuff? What do we have to do to it? We have to program it. We have to tell the computer what we know for it to know stuff. Computers they're not smarter than people. They're able to figure things out quicker than people. We still have to program the computer. So, we have to program it. Program it. That's what we must have to do. And so what are we going to program it with? If we want it to tell us how stars evolve, it better know what a star is first. So number one, we have to tell it that a star, let's say stars, are what? Big, hot balls of gas. All right, computer, stars are big hot balls of gas. Now, a computer's going to have to know what you mean by big, and that's easy. You can say, if it's over this size, it's going to be big. Computer's got to have to know what hot means. I mean, you're going to have to tell how you think, how hot stars are. You have to tell the computer that. Balls. Computer has to know, what a ball is. But even animals know what, play with balls, know what balls are. Everybody plays baseball. Everybody knows that. So it's easy to tell a computer about what a ball is, a spherical body. And then gas. Tell the computer what gas is. A computer's going to have to know what gas is. We can tell the computer that. And then we have to tell the computer how we think these stars hold together. How do they hold together? What force? Gravity. So computer, we better tell you the law of gravity. So you got to know that. Because we think that's how stars function. That's what holds them together. Then, computer, you have to know about laws that pertain to gases. There are certain laws that pertain to gases that tell you if a gas is a certain pressure, what the temperature would be, or if it's a certain temperature, what the pressure would be. These laws that pertain to gases, you know what they're called? Gas laws. The computer has to know those. That's how we think stars, or that's the laws that govern stars, the gas laws, because stars are big balls of gas. All right, finally, computer, we have to tell you how we think stars shine. How do stars shine? We think there's some sort of reaction in the core called fusion that we'll get into. So we think that's the case. And this fusion has to do with the nuclei of atoms, like where the protons and neutrons are. So we have to tell the computer what we know about these nuclei and the laws of these nuclei. So they're called the laws of nuclear physics. So that's what we have to do. We have to program the computer. And the computer's going to know this stuff now, because we think that's what governs stars. And then we're going to ask the computer, okay, computer, tell us how stars move on the HR diagram. Tell us how stars evolve. Tell us where one star goes, because a computer can speed up time and make it really quick. I mean, billions of years for us could be a second for the computer. Well, when we ask the computer to tell us how stars evolve, the computer still doesn't do anything. You know what the computer needs now? It needs something called initial conditions. What this means is that we have to tell the computer like how much gas we have to begin with, what the temperature of the gas is, what the density, what the magnitude is, all this, and then have the computer make its own numbers and kind of fudge around with different numbers and see what happens. So here's what we tell the computer. Okay, initial conditions. Let's start with we have a mass, number one. We have a mass of hydrogen and helium, H and He gas. Let's say it's, I don't know, X light years across. It should be across. X light years across. So we start with that. We put in the number like X. For X, it could be variables. We can start, you could put in a 20 light years. We can do one that's 10. We can do one that's 5. Well, at the computer, we don't want to figure this out. I mean, they say, hey, okay, computer, generate random numbers, put them in for yourself. We don't want to have to do this all the time. All right, computer. Let's say this mass of hydrogen gas is X light years across. Let's say it's Y, variable Y in mass. Let's say the whole cloud, I don't know, a billion solar masses for this whole cloud. Let's do another one, who knows? Billion's a lot. Yeah, we could put that in there. Who knows? We could put 500 million. We could put 5,000. We could put a whole bunch of numbers. All right. We could have the computer generate its own. So that's mass right there. It's mass. Y mass. Let's say it's T, variable T in temperature. Got to tell the temperature. Kind of shake that up a little bit. What about it's M in magnitude? I don't know, like absolute magnitude. And what about 5? It's D, variable D in density. Density is a matter of compactness. Density. It's how compact something is. So, all right, computer, we pull out these numbers, then go to work. So the computer's going to know about the gas laws, the law of gravity. It's going to know if there's mass together. It's going to condense it. It's going to know how the brightness increases because of the gas laws. It's going to know all about this. And if we put in different numbers here, it's going to kind of be able to create. Here's what our command to the computer is. Create model stars. That's our command. A bunch of them. And what we want, we're going to have this. Once we tell the computer to create model stars, say, okay, computer, what we want you to do is on this diagram, show us what happens with these stars. And on this diagram, we're going to have to do this. We're going to put a temperature here. So let's say the temperature is getting hotter this way, absolute magnitude, getting brighter this way. And you know what the computer shows? This is interesting. Computer shows that stars begin their lives way over here, in a region over here. If it's over here, you know what that means as far as temperature? Cool. If it's way down here, it means not very bright at all. And what happens, because the computer knows that these things are kind of showing how these things become stars, and these are points, they're necessarily going to become stars, the computer shows this. These things actually are not stars yet. They do this. Move here. So a bunch of them. The computer shows a bunch. And this is what happened in real life. I mean, it would happen with hundreds of thousands, millions of years. Computer shows it in fractions of seconds. So, I mean, we could slow down the computer if we want to and make it last a little longer. But then the computer shows that these things that started over here in this region end up moving. Their properties change until they get to somewhere over here, and then they stay here for a while. And they end up in a region that's right over here. Look at this. So those things end up over here and stay here for a while. Well, look at this. The computer then shows that it might stay here for a while in the computer. I don't know how long, but it could be billions of years our time. Then what the computer shows is that some of these things that became stars from here start going this way. Look at this. And end up here in this region. For not that long, but a little longer than they took to get up there, these things. And then the computer shows some of these model stars that are up here end up going, look at this. This is kind of weird. Some of these end up here. And right here. Look at that. And some of these actually, you know what happens to these? Some of these, actually most of these, end up dropping down here. And then up here. So look at this. When we're done, what the computer showed is that these model stars, not real stars, it shows what they do. And wait a second here. Doesn't this look kind of familiar? Have you seen something like this before? I've seen something like this before. This reminds me of something. This reminds me, look, of that. Well, doesn't this look like that? But why? These were real. These were real stars. These were things that we saw in the sky. I mean, real stars. This is the HR diagram. The computer did not know about the HR diagram. We never told the computer about the HR diagram. We just had it plot on the same type of axis. So why do the model stars mimic what we see in reality? What does that mean about maybe how we program the computer? Doesn't that mean maybe we program the computer correctly? That what we think we knew about stars, we do know about stars? And the computer had the luxury, or we had the luxury of using the computer. What the computer does for us is show us quickly what stars do without having us, we don't have to wait for billions of years. So now, think about this. Doesn't that mean that now, I mean, this must be accurate? I mean, doesn't that mean because it mimics reality? If we program the computer with a whole bunch of BS, wherever that happens to be, with all these laws right over here that didn't even pertain to stars, why would reality, that's not reality, why would reality be matched by our model stars? There's no way. If we kind of did a whole bunch of stuff that didn't even make sense, we might have, these model stars in different, all over the place, or different groups. It wouldn't make sense. But since it matches reality, we think we know what governs stars. But what the computer helps us with now, kind of like a calculator, or other computer for other things, it does things for us quickly. So now we can see. Let's look at what we see for the sun. The sun was born somewhere over here. Let me do this. And let's say this represents, I don't know, this represents the sun right over here. Let's say that's the sun right there. The sun right there. Sun. Well, you know what it showed? That the sun came from here. We're going to talk about this region next time, what that is. So the sun came from here, and it wasn't a star really until it kind of ended up here. Something's going on with it to make it kind of stabilize. And then what the sun is going to do eventually, we don't have to wait for this, it's going to end up here. What the heck is that? Remember what this was? Oh, Yeah, the giant. And then what's going to happen to the sun, according to the computer? It's going to end up here. What's that? White dwarf. So we think we know exactly what's going to happen to the sun. And not just the sun, every star we see in the sky, we know what's going to happen to it. Now, we'll never be able to wait that long, but we think we know what's going to happen to it. And that's the beauty of this, which is called computer modeling. Computer modeling. Computer modeling helps us figure out what's going on with stars, what's going to happen to stars. And this is incredible. So we have at our disposal this tool, computers now, to help us figure out what's going to happen to stars, the sun and other stars. And we're going to get into this. We're going to start talking about this place first, where stars are born, also how they're born, and then talk about their lives. And then eventually, after their lives, you know what happens? Their deaths. So that is it, and we will continue next time.